All right. Yeah. It has been recorded now, and some of you, if you come late, then you can view the recording if you want. So hopefully, how many of us here now? Yeah, around half of us. So it should be all right. Let's start. Okay. So first I share my computer screen. There are a few things I need to talk, right? There was an error in the assessment. I didn't realize that until today when Anna, I think some students, they had some questions regarding what's going on. What that is, I want to show you now. Okay, just to make sure. So everything is same, just the one line, there was an error in writing. Hopefully you can see my computer, yeah? It's good. So this question number 2, the task 2, intersection analysis task, and the 2B. So it was supposed to be when right turning lanes are added on east-west road, it was before north-south, which was wrong because we already know north-south road has already the right turn lanes there. That was an error. Yeah. So what that mean? Can I just use little bit to explain what are the options you gotta do? Is okay? So first case is existing case. Oh, where is my sensor? I want to connect to my computer. Please do ask questions. Hey, make little bit informal. If you have any questions, you can ask anytime. Let's do that. Okay, here you go. What happened there? There you go. So in the task to intersection analysis tasks, we need to do 4 tasks, I think, yeah? Task 2A, we need to analyze existing intersection, existing unsignalized intersection. We need to analyze. I think based on the description, if you want to quickly see that, the road is like that. Intersection is this way. North-south is the major road, and there are already right turning lanes here for the north as well as from the south, separate lanes for those movements, right? All others, there is a separate lane, and then through and the left, they share the same lane, right? Over here as well, through and the left, they share the same lane. But from east-west, currently, only one lane to go left, through and right. Same as from the west, only one lane for the all 3 movements. So this is the first analysis you need to do it. So task 2B is modified based on the information we have. So we also add one right turning lane on east and the west. Yeah, road is like this, intersection, right? Yeah. So there is separate right turning lane from the south, short lane. That's the existing case, right? Already there. We can just to remove some of the issues, we can also we have introduced the right turning lane from the east-west as well. What that means? All the traffic through and the left sharing the same lane, through and the left sharing the same lane everywhere. Same lane. This is the modified case, right? Yeah. So third, 2C is just a single lane roundabout. Remove everything and analyze for the roundabout. And a 2D, for the case, we need to design signal system for this intersection. Modified unsignalized case, that's the layout of the intersection. We need to design the traffic signal for this case. Is that clear now? Yeah. So that was supposed to be, there was an error, so I tried to.
Excuse me, sir.
Yeah.
When how to divide that volume for new added lane?
You don't need to. There is already volume given for the turning movement. So just that volume goes there. If you, okay, just let me, so keep this for now, yeah. If I open up, not that one, this one, yeah. If you open up, volumes are already given here. You see? That's a volume are based on this configuration. So those volumes represents the turning movement. So it does not matter where that we allocate those lanes, right? Yeah. So if I see from here, did you see? Can I? Yeah, thank you for asking. Maybe I'll just do one. Yeah, just to make sure you understand. So what we need to do is, so what is the traffic volume? If you read here, just wait. Yeah, I want to see. Okay, let's say this is the traffic volume data here. So let's say from south, 50 left turn. So there's a 50 here. $50 left turn from south. That's 50 there. And then what's 500 through? And then 100 right turn in this 100 there. From the east, 30 left turn. So 30 left turn, 15 through, and right turn based on your student ID. Let's say you got 5, just in case there. You see, similarly, you can have, because volume doesn't change based on the information intersection configuration. Is that clear now? It's good? Please ask questions if it's not clear, right? Volume does not change. Of course, traffic volume is there. It does not change based on what type of intersection configuration we have. Volume is same, just based on the layout, lane layout, then the capacity level of service may change. That's the reason why we need to improve the intersection.
Then we have to just add the short right turning lane in both east and west lane.
Yeah, this is the second case. Yeah, modified case. At the beginning, existing case analysis, there is only one lane, just analyze for that case. Good. For the modified case, just add extra lane to the east and the west road as well, and then analyze it, whether the capacity improves, level of some service improves or not, you can check. Yeah. And the third case, you design a roundabout for this traffic volume, and you also design the traffic signal system for this configuration of intersection layout.
Excuse me, sir.
Yeah.
For task 1, see how to we can divide the segment. There are 2 TRD for basic freeway.
Yeah. Question 1 you're talking about, yeah?
1C.
1C. All right, yeah. Proposed freeway, yeah. So what was the question?
How can we divide that 2.5 mile road segment wise?
Yeah, no, you don't need to divide. There is only one segment, yeah. This is very simple analysis. It's just the basic segment of the freeway, isn't it? Yeah. So you don't need to divide and do the free-val. I'm not that much interested for free-val. I'm interested for here. Of course, you can use that to verify your answer, right? Yeah. But that's not what, because there is only one section, right? Only one segment. You don't need to divide because there are, we don't know on ramp, off ramp, you know the details. We don't have anything of that. So just assume one basic segment and then you calculate. It will be like a very quick. It's good?
Good, sir.
Okay. Thank you. All right, guys. Yeah, thanks for this. Thanks, Anna. I think, yeah, you sent me an email because I didn't check all. I thought I gave the good information, but there was a little bit mistake there. So now I corrected it. I have uploaded again. So please check the recent file. Is okay? So that's done. Now let's learn about third type of intersection roundabout design. Design of the traffic signal, not signal. Signal I'll do on Friday. I'll do today if I can, how much I can cover. Let's learn about how to analyze the roundabout manually, right? We have learned to analyze roundabout using Sidra already. It's quite easy, really, Okay, but let's do manually using equations, and then we can compare the solutions. Okay, first thing is here. So roundabouts. These are the contents. Roundabouts. Where we can use roundabouts, I'll briefly talk. Geometric design. I'm not going to do that much because it's just a layout there. I would be covering a lot of detail about how to analyze whether particular roundabout is doing good or not. Yeah, we need to verify, right? Of course, your problem when you start working will be, oh, that roundabout is maybe not working, a lot of delays there, people are frustrated, they have complained. Can you check whether that's the case and what we can do for this? That may be the question, right? When you start working in any traffic area, in local areas, right? So that's what I will be doing today. Most of the things I will be doing operational analysis of roundabouts. Of course, there are other considerations, pedestrians, line marking, lighting. They are mostly the standards, right? So that means we hardly change anything. Learn with of that. You need to provide light there and there. There is a rule how to use roundabout. You see, those type of things are most of the default. But we need traffic engineers' knowledge to do the analysis of the roundabout. That's what I will be covering today. Okay. What is roundabout? Of course, it's a one form of intersection. Really, roundabout operates as a series of T intersection, right? If this is roundabout, you see, over here is like a T. That's a one continuous road, and then that's the T road. Same thing from the east, continuous road, and then it's a series of T intersection around. Yeah, it works in that way. So mostly the roundabout have been proven to be very safe and efficient of intersection control. Not everywhere, but some situations, they are really good. So this is the configuration. Of course, we already know because we have been using the roundabout a lot when we drive, right? We call this in the center, is that at the central island. Mostly central island is circular, but some of the times because of the land situation, sometimes we can have slightly oval. But we would recommend to have as circular as possible. So when you enter to the roundabout, we call it entry curve. And this is, we call it holding line, where you give way to the circulating traffic, yeah, who is coming from your right. And then we curve it. There are two reasons for curving it. One is the slowing down of the speed. Another is making the angle of circulating flow and the entry flow is small. You know, when the angle of two flows is small, then relative speed will be smaller. So even if there is a crash, there is a less chance to be very severe crash. Okay, so that's the reason, two reasons to make it curve. So there are some islands to separate, yeah, like that. We call it splitter islands. And then when you get out, that's what we call it exit. That's going in the entry from all sides of the roundabout. Sometimes we have like a median separation like that. Sometimes we just have a line marking, but there should be a little bit of something that helps for the pedestrian to cross as well. Just hold there and then cross other side. So this is the fundamental roundabout configuration. Please ask me questions, hey, if you need some clarifications. When the roundabout is best. Okay, that's what this slide says. It's a very old slide, but it's still useful. When we call by arterial roads, it's about 80 km speed. When sub-arterial, it's around 70 km. Collector road around 60 km/h, and then local road 50. Look at here. Roundabouts are very good when connecting with what? Local road with local road. You see, two roads are connecting 50 km/h. That's the very good application. It is also good when collector roads meets the collector road. Did you see? Collector road meets the collector road. But they are not good if one road is arterial road carrying 80 km speed, other road is like a 50 or 60. That's not good. They are not good. The reason is because the main road carrying heavy traffic, They keep on coming, and then from the side road or smaller road, people can't get into the roundabout. And then a lot of queue happens in the minor road. So please check this slide. When you design the roundabout or suggest roundabout changes, always look at, how much is the speed of 4 roads connecting? So what's the volume? So we need to see where the best location, that's given here, right? A is the best solution. B is okay sometimes, but C is not that okay. It's good? Now, first thing, right? If the roundabout only single lane means single lane going in and a single lane circulating traffic. We try to make 90 degrees as possible. If there are 4 legs, please make like this connection, right? All connection, all side 90 degree, and put roundabout there. It's very, very good for the visibility perspective, as well as people, they don't confuse when they drive. If more legs, please don't provide too many legs, because I have seen some roundabouts around, 5 or 6 legs. They are very confusing for the drivers. If multi-lane roundabout, that means 2 lanes going in or 2 lanes circulating or more than 2. What we need to do is, you try to limit the number of legs to 4 and arrange in the 90-degree fashion. If more than 4 legs, please, don't do that. It will be even confusing for multi-lane, more than the single lane. Another terminology is central island. You see the island in the center. Please don't plant very big trees in the center to obstruct the visibility. Some environmental people, they may want to plant trees and things in the center. There's a empty space, but that is not the case, because we need to see clearly, right? Who is coming, we need to give way to. That's good. How big the roundabout depends on the space and the speed. Higher the speed, bigger the diameter of the roundabout. The larger central island is the better geometry. It lowers the relative speed, also greater entry capacity, and then there is a greater separation of conflict points. Usually for local and collector roads, where roundabout is the most suitable, we provide the central island with a diameter 5 to 15 meters. Some are very small, like 5, or some are up to 50. But arterial roads, we go up to 30. Very big central island is not necessary. So circulating carriageway, how many lanes circulating traffic around the roundabout? So usually number of circulating lanes must be greater or equal to number of entry lanes. So if entry lane is 1 going in, there should be only 1 circulating lane. I have seen some roundabout 1 entry lane with 2 circulating, but that's also not confusing. It is okay to provide, but it's better to provide the equal number. Equal is better all the time. It's good? Yeah? I think you can read these informations anyway. I'm more interested in analysis and engineering aspect, right? So of course, we need to have the splitter islands, entrance and exit curves. We need to make sure that there is a shelter for pedestrians, control the speed, and guide the traffic around the roundabouts, and then just runaway right turners quickly go through the left. Okay, we need to prevent them from just, you see, some people are so stupid, right? If they are going from here in the roundabout, they are turning right, they don't want to circle, they just quickly run through. We need to prevent that from happening. It's not good. Okay, from the side distance perspective, 3 criterion should be met. From the criteria 1, we should be approach side distance, right? We should be able to stop before that holding line. You see? So that's coming speed, and you need to stop by that. You need to be able to see who is coming to your way, both sides. So that's a criterion 2. 3 also, it should be visible from the second car to get into, because if that is coming, otherwise they can go at one time, 2 cars like that. So we need to meet this criteria. So what we need to do now, Sorry, guys. Yeah. We don't plant trees here to obstruct the line of sight. We need to make sure it is clear there as well as here. There you go. So these are the stopping distance for different speeds. Yeah, in the table for lazy engineers, but we know how to calculate distance, right? What is distance? Stopping distance, SSD formula from week 1. Yeah, what? Vt plus v square over 2z d plus minus d. If you solve in that, you get similar to these values. But this is just for the quick check. So this is, I took this data from Sidra. Sidra guys, they have done a lot of the geometry measurement around Australia. This is the summary, right? Look at here. Average entry width was 8.1 meter. Average number of entry lengths were 2. Yeah, that's the entry width, circulating width, inscribed diameter, entry radius, and then entry angle. You see, that's the average. Sometimes very maximum, minimum. So they collected all the geometry data and presented here. That's interesting. They have another for multi-lane roundabout as well. All right, let's do next. Now we talk about stories. Let's do the things. All right, let's calculate. What we need to do is, these are the steps we need to follow to analyze roundabouts. They are more or less similar to unsignalized intersection we covered last time. But let's, number 1, assemble the traffic data. Yeah. So we collect traffic volume data mostly, or peak hour factor, how many trucks are there, passenger car equivalent, so many things, right? So determine the number of entry and the circulating lane. Based on the configuration, how many lanes to get in, and then how many lanes in the circulating traffic. You need to find that first. For single lane roundabout, this 1 and 1. Very easy, right? So record the geometric values like inscribed diameter, entry width, circulating width, those type of stuff. But believe me, these will have no effect in our manual analysis. But Sidra has taken some factors into account when they provide you the final results. So that's another reason why Sidra outputs and our manual calculations are not exactly the same. There will be slightly different. So we need to classify the entry lane type. If there are 2 lanes going into the roundabout, one of the lane dominates. Based on the Australian standards, the lane with highest traffic volume dominates. So we need to find the dominancy. That also doesn't have an effect, doesn't affect our manual calculation, but Sidra has used that system as well. Estimate the critical acceptance parameters, that is TC and TF. Critical gap and a follow-up time. Usually, critical gap for roundabout is taken as 4 seconds, Australian standards, right? And then follow-up time is taken as 2 seconds. I'll show you that, yeah, in the table later on. We want to see the characteristics of circulating flow. If the circulating traffic, right, on the roundabout, if circulating 2 lanes, then headway between the vehicles is 0. If there is only 1 lane, so these vehicles are separated by around 2 seconds. That's the same rule we use in our traffic flow analysis. Yeah, 2-second gap between 2 vehicles in the single lane. We calculate absorption capacity. There is a formula for that. And we calculate degree of saturation. That means what? Given volume divided by capacity. And we calculate delays and a level of service. And then we calculate queue length, how long the queue for the entry of the roundabout will be. Is this good? Yeah, so these are the steps, 10 steps we follow in our analysis. Please, in your assignment, follow these steps. Okay. So this is the exercise 2. That's the same exercise we did in our Sidra. Yeah, let's do this here. It's okay. So exercise tutorial exercise 6.2. So this is the roundabout. From the south approach, 50 are turning left, 100 straight, and then 50 right. Same, all others data given. That's the volume data, traffic volume. Okay, so if no information provided about the flow rate or the peak hour factor, then volume will be the flow rate. You need to change in SIDRA 60 seconds analysis. Oh, 60, yeah, 1 hour analysis anyway, right? The same thing. So if the truck percentage is less than 5, usually we don't need to worry about that much. Yeah, but if a lot of trucks are passing, then we need to change them into equivalent passenger cars using these two rules: 2 passenger cars for single unit truck, and then bigger trucks, articulated trucks, we convert by 3 passenger cars. So we convert everything into passenger cars and analyze it. Okay, so let's follow the steps, right? Step 1. I have developed the table solution. Please use the formula and then put the values in the table. Is that right? In your assignment. So first is step 1. I just collected the data. How I did that is here. Did you see that? I write the approach. I started south, going east, north, and west. Similar to what I did in my intersection analysis, unsignalized intersection analysis. So there are 50 vehicles turning left, 600 through, and 50 right. And then all others data also I have summarized. These are the given data. In your assignment, you have also this data already. So now, so entry flow, how many coming in? You sum them all. How many coming from the south? How many total? 600 plus 50 plus 50 is 700. It's good? Yeah? So you sum them all, 50 plus 200 plus 50, you put there. Yeah, 50 plus 600, 400, 1050, 50 plus 200, 400, 650. That's a total entry flow going from the each approach. It's good. Now you need to calculate circulating flow. How many? So what is the circulating flow? Now, can I just remove those my writing and I explain? Please understand this. Okay, you need that. How we calculate circulating flow. So circulating flow is nothing from the south. Who they need to give way to? Come on, if you are coming from the south, who you need to give way to in the roundabout? Who is coming here? Whoever comes at this location, we need to give way to. Yeah, so who is coming here? This 50? No, because they will be going that way. This 200? Yes, when they go through that, 200 is okay. How about 50? How they travel? So they go here and then turn right like this, right? So they also pass from here. So 50 also we need. So how about that 50 from the north? They go that way. So we don't need that. 600, they go like this. So they don't come to this point. So we don't need that. But these 400 guys, they come like this to turn right. That's why we need to consider 400. So how much? 200 plus 50 plus 400. How much? 650. Did you see? Circulating flow is 650 for the south approach. Did I explain all right? Let's remove one and do one other. Let's do for the north approach, right? Circulating flow for the north. If you are coming from the north, who you need to give way to? If you are coming from the north, you would be giving way to any vehicles passing that particular point, that point. Who goes there? That 50 not, this 200 yes, and this 400 also yes. That 50 no, 600 no, because they go this way, they don't reach that point. They don't need to give way to. That's 50 guy yes. That's it. All others, they don't need to. So how much now? 200 plus 400 plus 50. How much? 650 again. From the north, 650 again, circulating flow. Is it clear now? Yeah, please calculate circulating flows that way. So just think who you need to give way to, which flow. All right. So now you fill in here because we need that. This is for vehicle per hour. We need that for vehicle per second. That's why I just converted into that. Yeah, divided by what? 3600, I think. Yeah, vehicle per hour to vehicle per second. It's good. Yeah, that's we need that for the formula. That's why I put here at calculation. So first thing is you need to calculate the circulating flow. Circulating flow is equivalent to conflicting flow in our unsignalized intersection. Exactly same. Who they need to give way to. You think you can do? Or do you want one more explanation for another approach? Looks good, yeah? You are not talking? I'm not sure, right? Let's do the west now then. Yeah, just to show you. Let's do east. If you are coming from the east, you need to give way to any vehicles. They are coming this way, right? At that particular point, that side. So who they come from that point is, of course, this 600 they come, 50 they don't come, 400 they do. And then they 50 they don't arrive that point, 200, but 400 they do. Okay, so how much? They will not, because they go that side, they go straight, they go to the right, they don't arrive to that point when you circulate. So what that mean? 400 plus 400 plus 600. How much is that? 1400 for the east. East traffic is a 1400. That's how we calculate circulating flow. Done. Next. Number of entry and the circulating lanes. You see here, if there are two lanes, oh, come on, yeah, if there are two lanes coming in, yeah, there should be two lanes circulating. Sometimes if there is one lane coming in, two lanes circulating is okay. But if two lanes coming in, one lane circulating is not allowed. Otherwise, they will just go in the same place. That is not good. It's good. So the best idea is make sure number of circulating lanes are equal to number of entry lanes. You can check quickly check how much we need based in this the diagram here. You see, that's an entry flow. Let's say entry flow is 1000 in one case. And if the circulating flow is 2000, where they meet most probably, you see, most probably you need two lane roundabout. Within this, single lane is enough, and then three lane, but oh my goodness, three lane roundabout is a lot complicated, and then they require a lot of space. It's good. That's for the quick check. In your assignment, I have specified single lane roundabout anyway. You don't need to look at this figure. So based on the given geometric value, we can also identify number of lanes. So if there is only, if the entry width is about 6 meters or less, there will be only one lane. 6 to 10 meters, there will be two. And then if we haven't, if we haven't separated that, of course we have, most of the time we do. So then it's okay, we need to fix that way. Also the circulating lane, they have the different width requirement for different number of circulating lanes. In your case, in your assignment, just one circulating lane and one entry lane. Lane type, that's what I mentioned before. If there are two lanes coming in, one of the lane dominates. Okay, so that means usually entry lane with the greatest flow is chosen to be the dominant stream, but we don't use that in our manual analysis anyway, but CDRA has some factors in it. So now let's solve now from step 1 to 4, all of those combined now again, right? Look at here. Step 1, I already explained that. Did you see the traffic, collect the traffic data? And at 2, 3 inscribed diameter, I just assume 15. If nothing is given, don't worry. Just you can assume anything within the boundary. Of course, we are not using this data for analysis later on. So this is the based on the condition, what is the circulating flow and the entry lane type, you can mention. Okay, these all values have no effect in our manual calculation. You can summarize if you want, or you can not summarize as well, because that's is included in Sidra somehow by factor and things, not equations. If there are equations, I would tell you. Yeah, but some factors and other things they have used there, but for us manual calculations, we don't have that. So let's do the next step. What's the step number now? 5 and 6. Critical acceptance parameters, gap acceptance parameters, which is critical gap, TC. Again, the textbook are different. Sometimes they call it TA, right? That's the same as TC we covered before. And that TF is a follow-up headway. Yeah. And then minimum headway in the circulating traffic is if there is only one lane, it should be separated by 2 seconds. If more than one circulating lanes, we use the tau value 0. It's good. These are the Australian standards, right? We use that for the analysis. If you in Sidra as well, Sidra automatically takes the values, but there is an option, you can modify for these values. So now, this is step 7. We need to calculate capacity. Let's do one example. Come on, guys, you are ready, right? Yeah, you have ready calculations. Can you calculate that now? Let's do for the single lane roundabout. Let's do one example, right? What we have. So we need the circulating flow. Circulating flow, let's say I want to do the south approach. Circulating flow is 650. Can I do that now? Circulating flow is 650. What is the circulating flow? Here. So I can show you in the figure, but you need to use this equation for the assessment, all right? But this figure also gives the similar answer. 650, where is that 650? Somewhere here. And I go up and I put the single lane roundabout. And then this is the single lane, right? That line is single lane, that's a multiple lane. So you just go there and read it. How much is that? Around what? 950 around? Yeah. But if you use these equations, you get the exact value. Let's use the equation. Could you please compute? So QP is the priority flow in meter per second. Tau is single lane roundabout, that's 0. And then TA is 4 seconds. And a TF is 2 seconds. And a QP is, this is the meter in the vehicles per second, right? I want to check for that. So 0.181. So QP is 0.181. If you press in the calculator, you get the value very close to 950. Please use this equation to calculate capacity of the roundabout. This equation is when tau is 0, this equation is same as what we used before. Yeah. It's good. You can press calculators, yeah, later on. Let's move on. So now, absorption capacity, this is from Sidra. Okay, Sidra, guys, we analyze that. So absorption capacity based on the circulating flow. What is the entry approach capacity? Upper bound, lower bound, typical values is given here. Okay, instead of these curves, right? This is a similar curves, but this is from Australian standard. Yeah. But over here, they have slightly modified based on what they observed. Same thing is the 4-3 lane here and a 4-2 lane roundabout. So let's see. Now, next step, we need to calculate degree of saturation. Degree of saturation is nothing. What is the incoming flow divided by capacity? We already calculated previously. Let's do it. And then we try to make degree of saturation about 0.8 to 0.9. What that mean? About 80% of the theoretical capacity is the practical capacity, usually, right? 80 to 90%. We try to make it. I copied all the solution again here. Yeah. So now, in this case, you see, I already discussed up to that. And then this is the follow-up time, is the critical gap, and then there's the headway. And then we got that value here. So from the equation, right, use the equation, or you can use figure, but equation gives exact value like this. In this case, 955. Using the figure, how much we got before? 950. Did you see? Very close enough anyway. But please use equation to calculate this. These are the capacities. So step 8, degree of saturation would be what? Entry flow. What is entry flow? Here you go. 700 divided by 955. Can you do that for me to check? 700 divided by 955. How much you got?
0.733.
That's it, right? You see, that's how we got the degree of saturation. Incoming flow divided by the capacity. It's good? Now, if I observe here, if I see the degree of saturation, these are more than 1. What happened? What is the what do you interpret this? What do you understand by that? Incoming flow is more than capacity. What happens there now? Of course, queue up, right? People queue up in the roundabout. Yeah. So please don't design that. Try to make from 0.8 to 0.9 for all degree of saturations. That is our aim. Of course, less than 1 is okay, but that's very critical. If something small thing happens, of some stupid guys, they don't go in the gap, or some people they just don't afraid to get in, then what happens? There will be a queue. So we try to make about 80 to 90%. In this case, other two looks all right. What that mean? South and west approach look all right, but north and the east approach, we need some attention. It's good? All right, let's move on now. I cannot go ahead without changing because it's already roundabout is degree of saturation F, right? Because the two sides are already bad. To continue my analysis, I need to make sure they are below that. So I just artificially change this way. Did you see here? Oh, that's the point, right? I want to discuss that. I already discussed anyway, but yeah, let's see. What is that? You see, because entry flow is 300 here, we got capacity 264. Entry flow 1050, we got capacity 955. So they have the degree of saturation more than 1. Okay, now we need to calculate. There are 2 types of delays at roundabout. One is queuing delay, when the vehicles queue up to get into the roundabout. Another is geometric delay, when because you need to circulate, you need to travel a lot of distance in roundabout, then the straight turning. So that's also another delay. So total delay is included queuing delay plus geometric delay. But geometric delay is usually constant, so we are not that much interested. So we are interested for the queuing delay. So you calculate queuing delay to say the level of service, to specify the level of service. So who is good at math? Please use these equations, all right? To calculate queuing delay, that's the formula we need to use. Okay, of course, it's not hard if you make a spreadsheet and then put in. There's just a one sample calculation you need to show, and other you can just use that. But for the test or exam situation, please use the graph here. You see, this graph gives the very easy way to get the delays, because those equations are used to plot these graphs. This is for single lane roundabout. There is another graph for multi-lane roundabout as well. It's good? Yeah? So let's check one case, our case. What we need is we need the circulating flow, and then we also need the entry flow. Okay, for the queue length. So let's talk about one case in our area. Which one? Let's do delay, right? Yeah, so let's do that for the south approach as well, right? So entry flow is 700. And then circulating flow is how much in vehicle per hour? Circulating flow is 650. Let's take these two things, right? To check one case. 700 entry flow, 650 circulating. So circulating flow 650. Where is 650? 650 here. You go up. It's good. And then 700 is coming from here. Yeah. This is 600 and 800 in between. Let's join that. They meet somewhere. And then once they meet, you go this way. Oh, I don't know. Maybe what, 12 seconds? You see, delays for south approach is about 12 seconds from this graph. That is okay if you want to do in the exam situation or test situation, limited time. But you have plenty of time for assignment, please use this equation. They will give the exactly same value, similar value, right? But table, you can look from the table as well. I want to check, right? What we have that. What we have for the, what we got delays. Yeah, did you see? Delay is about 12 seconds. I got the same from the graph as well, right? But it's better for your assignment, compute using the equations. I compute here using the spreadsheet and the equations, so I got the exact value. All right. Once you find the delays for vehicles, use this diagram to classify the level of service. This table. Level of service A, if you need to wait less than 10 seconds to get into the roundabout. B, if 10 to 20 seconds. If you need to wait more than a minute or 70 seconds, level of service F, we are doing bad. Or also the degree of saturation is more than 1. In that case, we need to do something about that roundabout. Easy? All right. So that's how we calculate. And then I check the table and then loss B, AA. Why I got AA? Because I modified the data, guys. Believe me, I changed that 400 to 40. Yeah, otherwise I cannot calculate that. Did you see here? It was 400 before, and I tried to change to 40 so that I can compute. Otherwise, what happens? Can I show you one thing, the delay calculation? Let's say, if, let's say, 955 is the capacity, and then 1050 is the entry flow. Let's say circulating flow is 650, entry flow is 1050. If I go here, circulating flow is, how much was that? 9 something. It goes out of the graph. So we can't calculate those, right? It's a very long delay. So that's why I just changed the data there to make sure you have some calculation. You cannot change the data like this. So if you got that something bad, so you need to write level of service F here. It's good, yeah? If you have like a degree of saturation more than 1, level of service is always F. Oh, that's the pointed out, right? That's the one I changed things. So now interequivalence is very easy. What you need to do is, you know the average queuing delay, you just multiply by entry flow, and then you can calculate number of vehicles queuing up. Yeah, if you want to be 95 percentile sure, you just do that what? Rule of thumb, 3 times the average. So that means you calculate average from here, multiply by 3. If you get 1 there, then there will be 3 vehicles. I'm confident that 95% queue length would be, there will be maximum of 3 vehicles. That's it, right? Yeah, that's what we will be doing that. So if I do that and I use this, right? Did you see that? That's that multiply by what I did is QM, right? That in the meter per second. And then I got that 3. This is the average. And then I just times 3 to get the number of vehicles in the queuing. So after the modification of that traffic here, I just did that 40 changing to 40. So the number of vehicles queuing up highest would be on the south approach. Easy, yeah? How you feel? That's a lot systematically I have prepared. I have some calculations right in the table and the solutions. Please follow this, all the steps, and then give me a good report, whether hopefully you get very good level of service. If not, we will be designing the signal next. All right. I think that's it for roundabout. That's how we analyze the roundabout. Steps, follow, and then our job is to find the queue length as well as the level of service. Any questions for me? No? All good? All right. Hopefully you go over this, and this roundabout analysis is one of the easiest analysis of the intersection. because it's very easy to calculate conflicting flow, right? Because you need to just give way to the circulating traffic. And then once you have that, all standards there, all equations there, just follow each steps. And there are a lot of graphs as well. So this gives gives us the very quick things to compute. That's good. All right, I'm not saving this. And let's learn about traffic signals next. What time? Yeah, we have a little bit of time. I'll not cover all. I'll go partly and I'll finish up on Friday. Okay, signal. Oh, not that one. Where is signal? Roundabouts that's a signal. Signal is a little bit takes time to understand, so I try to little bit do, and then again I'll come on Friday and we'll finish off. Is okay? There you go. So traffic signal. Of course, this is a very simplified case. Okay. Sidra will do a lot of complicated analysis as well as the priority, phasing, those type of things. But I'll give you the theoretical background, how these Sidra were developed starting, but again, they use the corrections. So we want to know the fundamentals. That's what I'm covering today. So general, we need to consider general things as well as geometric requirements, where we need to put the traffic signals. And then what are the phase layout and the display sequence. And then we need to do the signal phasing. We need to do this. And then fundamental concept and a definition. Then how we time. What that means is how many time we should allocate for one movement, how long green, yellow, and red timing. Yellow timing is usually we do from the dilemma analysis we did in week 1. Okay, but they are mostly given, right, default. But green time and red times we need to design. Designing, there are 3 methods, Western methods in the UK, and the HCM methods Osrood. So I have combined this all and to make the systematic way of how we design traffic signal. Okay, of course, I'm not talking about electronic or electrical part of here. So I'm talking about calculating, okay, for these vehicles, this movement, that much green time you've got to give. And then they will, the other guy, electronics or electrical guys, they will program it. So, and that displays the traffic signal there. It's good. So this is the signal design process. Of course, reading through the process is not that good. We need to do the analysis and design things. They are the process, you can look at it, but let's follow that. So physical layout, we need traffic volume data as well as conditions, peak, off peak, if there is a crash data available or things, right? Because if crash, why that happened, because of the signal or not, we need to know. Design requirements, we need to have the separate lanes, we need to have the standards based on the curve radius, median islands also, painted, curbside, service roads, so many others we need to consider. What sign, payment markings, that all follow the standards. Okay, we can't change that. So, number 1, where we put the signal equipment? You see, this is the Australian standard. Where we need to put it, if the road is undivided, what that means is there is no physical barrier here. Primarily, we need to put the signal indication here. Or we can also put an overhead. That's the primary, we must have that. And then secondary, you need to put over there, the other side of the road in the corner. Or you can also supplement by the overhead. You don't need both of these, right? One of these would be enough. If you have money, then you can provide both of them. And then as other options, because sometimes these signals, they fail. So we need to have other options as well. So there is another locations we need to provide. You see, there are few locations we need to provide. But if the road is divided, if you have a median separation in the center, Australian standard says you need to put the equipment in the center, the signal indication here, not over there, or overhead here. as well as overhead here or there. And the tertiary is there all the time. So you see, we need to provide the signal equipment at the correct location. Display. We can't just put here, right? Somewhere here, signal indication or somewhere there. So you need to have the standards follow where we need to, because they need to be clearly visible, they need to be correct, and so on. So sometimes these equipments, they have their separate on pole, signal post, or you also have sometimes the overhang post or indications there. Sometimes if you want to save money, we can just attach them to the traffic light, right? Road lighting. You see? You can provide combination of signal as well as street light. Yeah, wherever, but it needs to be at the proper location we just discussed. Next. So now, three aspect signals, usually we show the red at the top, green in the middle, and yellow in the middle and a green at the bottom. Yeah, just check from today. Hey, go here and check. Is that the red at the top? And a green at the bottom, display. And then yellow in between. Yeah, not the other way around. It needs to follow some rules. Same thing, if there's a 6 aspect, means you have also the turning arrows. Red arrow, yellow, as well as the green arrow turning left and turning right. If the first indication is green, what comes next after green? What comes next? It comes yellow, right? And then it comes, and then red, isn't it, right? Thank you. You see? So this is the sequence we need to follow all the time, and back to green again. Yeah. So don't provide like a green to red and yellow. It needs to be, there are reasons why. We used to have yellow in between as well here. That we used to have there like a four aspects, right? Yeah, not 3, 4. But we remove that. That's unnecessary. Really, the objective of providing yellow here is the people getting ready to go. Okay. Some people are too hurry to go. That's why we try to minimize that. Okay. This is just, you need to prepare to stop or clear the intersection. Yeah, that is essential. Look at the terminologies here. I'm not sure whether I will be able to convince you or tell you everything what we need about this, but I'll go briefly and I'll show you in some diagrams, and I'll come back later on when we go over the steps. It's good? So first is movement and then phases. Okay, so what does that mean? Movement means, you know, right? Like a left turning movement from south, 1, 2, 3, you know, the movement numbering we did before. Yeah, that's what we need to do, the movement numbering. But remember, if there is only one lane from the south, let's say, only one lane, and then the same lane is used by left and the right turning. So you cannot have 2 movements. This is what? Only one movement we need to number, because they need to use the same signal indication at particular time. We cannot separate different signals for turning left and right, because they need to get, if they get green, both of these movements would get green. Or if they get red, they must stop, both of them, right? It depends on. So movement definition is a little bit different here. So we need to provide the movement numbering so that they are allowed, we can stop both of them at one time and then go at one time. Looks good, yeah? So that's how we need to provide the movements. And the phasing means, let's say, the traffic, some of the movement we stop, and then we allow the other to go. So that's the one phase. So when in the next phase, we stop this and then allow the other go. Those type of things, right? In sequence. So completion of the all phases, you back to your original position. That is cycle. So that's what we call by cycle time or cycle length. We represent by C. This is the sum of display green time plus inter green time, the time between the greens. for all phases. Intergreen time includes yellow time as well as all red time. Okay, and the display green is really how much time is used to display the green. Saturation flow is another terminology we need to understand. Saturation flow is, okay, let's say you are in the one approach, you got the green. From that lane, if 1 hour, if you get all green, how much traffic can pass through there? You see, all green for 1 hour. That's what we call by saturation flow. Effective green time, of course, there are some, at the start there is a loss, and there is a little bit of gain at the end after it turns yellow, because people need to clear the intersection. So there are some formula to calculate effective green time. Minimum green is sometimes if there is only one vehicle, we cannot provide 1 second for that vehicle, 1 second green time for that vehicle. Why? Because that's not sufficient to clear the intersection. So we need to fix some minimum time required, even though the demand is very low. Start lag, start loss, in lag, in gain, loss times, arrival means incoming traffic. Degree of saturation means incoming traffic divided by the saturation flow. Practical degree of saturation is about 80%. Movement capacity using that formula, flow ratio and a green time ratio. Okay, of course, it's very hard to clarify these things unless we do the problem. Okay, there's a diagram here. This is very simple diagram to explain what the phasing and those type of things are there. Did you see here? There are 2 phases. Let's start with that phase. You see, when one phase was all red, yeah, all red, and then they started green, and again yellow, and back to red. For the other, when it was red, it was green, it suddenly changed. Okay, now change into what? Yellow, and then back to red. But there are all red also need to introduce, because you see, don't just stop the yellow and allow other to go, because some people, they just cross over the line during the yellow time. They can't clear the intersection. So we provide yellow sometimes 1 second to second time, so that all traffic all signal get the red. Yeah, so that the intersection will clear. So combination of yellow time and a red time, we call it intergreen time. What that means is green of one phase to the green of another phase, right? Time gap between end of the green for one phase and start of the green for the another phase, we call it intergreen time. At this time, the people start going. Of course, at the beginning, they will not be very quick. So there is a little bit start loss there. And then once they make one like a progress already, so they will have the saturation flow. And then at the end, when it changes into display yellow timing, then what? Some people start braking, and there is but still some are passing through that. So there is a gain there. So did you see? Start lag consists of start loss as well as intergreen time. It's good? And at the end, and loss time would be calculated alpha minus beta. Of course, we will do that calculations and I will see that. Looks good? Yeah? Let's do now. Let's definition. I want to talk about phase now, because phasing is so important in signal timing. Look at here. This is the phase A, phase B, and a phase. Yeah, say again, somebody? Is it asking question to me or talking to somewhere? All right, yeah, there you go. So look at here. What happens here? From the phase A, what we did is movement 4 going left from the south allowed, and from the west straight and right allowed, because we can allow all this at the same time. Why? Because there is no conflict. And the next, You see, we stop the south traffic as well as we stop the right turning traffic. We keep going from the 1 we can allow and the 3 here. The reason is 6 is pedestrian movement here, right? They give way to pedestrian and they go that side. So we need to movement number 1 there. So we can have this third phase. And then we allow the south traffic to go both of them. That's the phase C. So phase is in one phase, a number of movements get the same signal indication. We stop some or all of them and allow other group, the green signal again, and then other group. So if A go to B and a C, did you see A to B, B to C, C to A? So we call it cycle. From one phase to another phase to another phase back to original phase. Cycle time, complete sequence of all phases. Movement, number of vehicles, they share the same lane usually. Display green, effective green, I believe I discussed that already. Okay, so we will be talking later on. Yeah, let's start one problem. What time? Maybe, yeah, okay, there you go. So let's do one problem, very signal phasing. Okay, don't wait here. Sometimes, yeah, there are a lot of information here I took from the standards, right? Sometimes two-phase system, you see only two phase. So it is a north-south. North-south is allowed at one time and the west-east is allowed other time. But here there are conflicts, right? Yeah, these guys, they need to, you see, wait in the green signal. And then if there is a clear, they can go, otherwise they can't go. We call it filtered right turn. Yeah. In this example, did you see that? So because south lane is only one lane, so we need to movement the number only one. So that's a 4 movement. This is the same direction going. They need to indicate at the same time one movement. So let's say that's a 2 numbering, that's a 3, and that's a 4. Oh, that is it. They are going through, so only 3 because both are going through. Yeah. We cannot separate out, right? So that's because you see, these through traffic from this lane, we cannot stop and other go, right? They are existing from the same, so it's better to have 3 movement. So in the first we stop both 4 and the 3, and then allow 1 and the 2 in the first phase. In the second, we stop 2, still allowed the 1 and let the 3 go because there will be no conflict there. And then we stop all and just allow the 4 to go because otherwise it will be conflict. So that's how we need to organize the phases. So now this is the phase A. That's what dotted line means, the filter right turn. So you need to wait for the through traffic to go and then you turn right or left. And there are a lot of sequence there anyway. Yeah. Okay, so these are the examples. We use the Webster method. That's the first starting method. So this is, we call it minimum cycle time is given by L divided by 1 minus Y. So L means lost time, sum of total lost time per cycle. So which is for all the phases. So optimal cycle time is given by that equation, and then green time allocation for each is given by that equation. Let's do one small problem, right? Look at here. Let's design just the two-phase system. We don't know the turning movement, nothing, right? Can I draw the intersection here? All right. So from the north, 800, 10 vehicles coming. Can I just do like this? Simple intersection draw here. I'm trying to design very simple two-phase system. One time I allow the north-south traffic. And then in another phase, I allowed the east-west traffic. It's okay. So how we find that timing, right? So from the north, how much traffic coming? So we need to calculate the ratio with the saturation flow. Okay, let's do that. So maximum of, I'm talking about north-south, right? North-south case first phase. Maximum of ratio, that to that. So what happens? 810 divided by 1800. And what is going from south to south? Oh, that's a south again. 750 over 2000. Remember, that's a 2000 is saturation flow. We are just getting this like a, what they call degree of saturation. All right. Can you compute this for me, please? What would be you getting? Maximum of? What is 810 divided by 1800? Come on, some of you. Compute for me.
0.45.
0.45 is good. Okay, thank you. How about the other one? So 750 over 2000?
0.375.
375. Maximum of these two values is what? 0.45. Is good? Yeah. So next. So maximum of, let's do the four another phases, which is what? East-west. So what is that? So it's 1470 divided by 4200, comma 1200 divided by 4000. How much is that?
0.35.
Sorry, maximum of 0.35 and
0.3.
0.3.
3. Okay, so maximum would be what? 0.35. You see, so that's the flow ratio, by the way. All right, we got just the flow divided by saturation. We get the maximum because we try to accommodate the maximum flow, right? Yeah, the B by C ratio or saturation ratio, degree of saturation. So we got that. Any other data given? Two-phase signal. So the intergain time is 5 seconds, loss time is 2 seconds. So if loss time is 2 seconds for one phase, for two phases, how many total loss time would be? 4 seconds? Because 2 times 2, right? Because there are two gap. First phase, there is a loss time here, and then another phase, and there is. Did you see this 2 times? We need to get the loss time to collect. Amber time, yellow time is 2 seconds. So let's calculate based on the formula. It's okay, loss time, right? So what is that? Loss time, this one. Intergain and amber time, and then that's another small loss time. That's what we call loss time per cycle. So total loss time we calculated based on that. So I minus A, can I do that? So 5 seconds is I, and then that's A. So that's a 4 second. Symbol I use is wrong. Okay, so I need to follow the proper symbol system, right? Can I write the equation now? L must be, so I minus A, which is 5 minus 3. There are 2 phases, times 2 plus 2 times 2. Is that good? How much it would be? Lost time, right? Yeah, how much is that total? 8 seconds, right? Total lost time is 8 seconds. Now we know L, we can use the formula now. You see this one. Let's calculate. This is the minimum cycle time. How much it would be? Cm equal y over 1 minus y. Oh, I didn't calculate y. So can I do the ratio of that? How much is the sum of those? 0.45 plus 0.35. Is it 0.8? Yeah. So you got y, you got L. So now you can calculate Cm, right? Yeah. What is the formula? L over 1 minus y. 1 over, L over 1 minus y. How much is that? L is 8 seconds divided by 1 minus 0.8. How much you got?
40.
40 seconds. You see, total cycle time is 40 seconds. Yeah. So now how much they get others, we can divide using the same proportion. Yeah. But usually this is minimum. Usually we use the second one, this one, for the optimal cycle time. Can you calculate that, please? CO equal 1.5 L plus 5 over 1 minus y. CO equal 1.5 L plus 5 over 1 minus y. Is that correct? Good. Can I do that now? 1.5 times. This is the minimum required time. 1.5 times L is 8 plus 5 divided by 0.2. Can you give me that?
85.
85 seconds. That looks little better because they're based on the flow. Yeah, this is the minimum, but optimal usually 85 seconds. So how much these guys get? North south get. Can you multiply that? So GI, I need to use formula. Sorry. Yeah, this is the formula. Can I use that now? Let's say G, first road was, what was the first road? North south. North south. Yeah, north south would be what? YI, for that what we got? 0.45. 0.45 divided by y is 0.8. Cycle time we use is 85 minus L is 8. Can you calculate how much green time, effective green time, north-south traffic get?
0.43.
43 seconds, right? They get 43 seconds. And then green time for east-west. Can you use the same formula? YI is 0.35, I believe. Yeah, divide by 0.8, 85 minus 8. Can you give me? Yeah.
34.
35, is that good? Yeah.
34.
35 seconds or whatever, right? Yeah. So if we add them, how much it would be? That plus that. These guys get green signal of that seconds, and that guys they get, right? How much is total? 78? Around, okay? Just roughly. Yeah. Yeah. So where the other one gone? Because we calculated cycle time for 85 seconds, but they get the green time for two phase. They get the green of total of 78. The remaining time is lost because we need to change from one phase to another phase. Is good? Yeah. That's how we calculate the simple analysis. Sorry, I wrote over. I think I have solution here. And that looks okay. Yeah. 40 seconds, 85 seconds, the optimal cycle time. Green time they get is 43 seconds and 34 seconds, right? So that's how total is 85 because lost time is 8 seconds. Yeah, good. This is a very simple, without any complex calculation. We need to get the flow ratio, Y, and then you need to calculate the lost time, and then just use the formula to calculate the cycle time. But that is not that easy when we analyze the complicated intersection. It's good. So for that, this is the process we follow. All right, I have written in a simple way here. Number one, step one, we need to describe movements and the phases. We need to develop the diagrams. Estimate the saturation flow. If it is given, then you just use that. If not, we can collect the data for the saturation flow from the intersection. We need to calculate the movement times, and we need to identify the critical movements. And then calculate optimal cycle time. Calculate green times for all of those like we just did, but a lot complicated. Yeah. So when we consider all those cases, and then calculate capacities, delays, and the level of service. I have written a note here. The process is iterative. We cannot just keep going and calculate and find the value. So what we need to do is we need to trial and error. Start from cycle time. We calculate all those. If something does not satisfy, we change the cycle time and keep updating the cycle time so that we will get the optimal cycle time at the end. So what I do today is I'll stop here and I'll follow this stepwise process and the calculations on Friday. I'll finish that on Friday. Any questions for me? Now we'll finish for today. Yeah, these steps I'll follow on Friday morning. Yeah, at 11. So we'll go through this, all the process, and then calculate the signal timing for our case. I'll also discuss the assessment, and then we'll do SHIDRA a little bit, and then hopefully we can be ready for your submission next week. Assignment 1 analysis task is due next week. Okay. Can you guys write your name and student ID in the chat, all of you? Yeah. Thank you.
Is there any chance the quiz can get extended to the weekend, or is it going to be strictly on Friday afternoon?
Oh, that's what I just did, Anika. Yeah, I
Okay,
changed
sorry.
up to midnight. I changed because that was I had a class during the day, and I thought, okay, maybe I'll just extend up to the midnight.
So midnight on Friday.
Correct.
All right. Thank you.
Yeah, all of you guys information, please check, right? I have extended the quiz to this Friday. So it will be from 3 o'clock to midnight so that you will have little bit of flexibility whenever you want to do. Yeah. Thank you. Yeah. Thanks, Anika. Yeah. All right. Anyone else? Please write your student ID and the name here. All right. Okay. Thank you. Yeah, see you on Friday. Yeah, and then what we do is Friday we'll finish this stepwise process, signal design, and then we talk about so many things other, right? Okay. Thank you. See ya. Bye.
Thank you, sir.